So here we have problem 1.1 from Fundamentals of Heat and Mass Transfer, and the problem is the thermal conductivity of a sheet of rigid extruded insulation is reported to be K equals 0.029 watts per meter K. The measured temperature difference across a 20 millimeter thick sheet of the material is T1 minus T2 equals 10 degrees Celsius. And then we have a two-part question. So part A says, what is the heat flux through a 2 meter by 2 meter sheet of the insulation? And part B says, what is the rate of heat transfer through the sheet of insulation? And we should notice here right away that we're asked for heat flux versus rate of heat transfer. So they're not the same thing. So we're going to start by writing down our knowns. What do we know before we even start the problem? And we can see we know K equals 0.029 watts per meter K. It's Kelvin. That's the thermal conductivity. We also know that the thickness is 20 millimeters. So I'm going to write thickness as T equals 20 millimeters. I'm also just going to put that in scientific notation, times 10 to the negative 3 meters. And finally, we know the temperature difference, T1 minus T2 equals 10 degrees Celsius. So we're going to say delta T equals 10 degrees Celsius. Okay, now what are we finding in this problem? So for part A, as we said before, we are finding the heat flux, not the rate of heat transfer. And the heat flux is going to be Q sub X, meaning it's in the X direction, and then we're going to put this double prime. That double prime, remember, distinguishes the rate of heat transfer from the heat flux. And similarly, for part B, we are finding the rate of heat transfer, which we will denote as just Q sub X, no primes there. So let's keep going. So next, we have to draw our schematic. So I am going to attempt to draw here a sheet, and it is going in 3D space, like so. We have T1 on one side and T2 on another side. And then we know K, and we can figure out the area. I'm jumping ahead a little bit, but because we know the dimensions of the sheet, we can eventually figure out the area, and we're going to need that. We know that this distance here is T, that 20 millimeters from earlier. We know that heat transfer is going from T1 to T2, which is going to be in this direction, and I'm going to call this the X direction, keeping what we said earlier. And finally, the last thing I'll draw is our actual heat transfer, which I will draw with a squiggly arrow, and I'm going to call that Q cond for conductive. So let's move on to our assumptions. So what are our assumptions? Looking at our schematic, we have one hint right here in that we drew this X direction and we drew our heat transfer only going in this X direction. So that's going to tell us our first assumption is we have one-dimensional or 1D heat transfer. And you could just say one-dimensional conduction if you wanted to be a little bit more precise. And then we're going to say in X direction. Then, as we will do for most of this chapter, we are going to assume steady state conditions. We're not diving into anything transient or changing with time. And the last thing is constant properties, meaning that the thickness of the sheet is not going to change, the K, the thermal conductivity of the sheet is not going to change, nothing's going to change. We're just going to keep it as it is. So now we're ready to actually solve the problem. So let's move down to our analysis. And first we need to find the heat flux. So for part A, we're finding the heat flux Qx double prime. So if we remember, we have our basic formula, Qx no prime equals minus Ka, A And some people write this differently, but I'm going to write delta t over delta x. Some people also put dt dx in that derivative form. And so you may remember that if we take this equation and we divide both sides by a, then the a on this side cancels out, the a on the right side cancels out, and that q sub x turns into q sub x prime prime, double prime, giving us that heat flux. So now we know our equation we're going to use for part A. We're going to say q sub x prime prime equals minus k, and no a because we took that away, delta t over delta x. And from here, it's pretty easy. We just need to plug in. So we have negative, and then our k was 0.029 watts per meter Kelvin. Oh, pen's going a little crazy there. Times delta T, which was T1 minus T2, which we said was 10 degrees Celsius, over delta X. And in this case, delta X is the width of the shape that the heat transfer is going through. So if we look back at our shape, we can see the heat transfer is going this way. So we need to figure out how much thickness does this heat have to travel through. This heat has to travel through T thickness. And T was 20 millimeters, so 20 times 10 to the negative 3 meters, scientific notation. And here, just to give myself some peace of mind, I am going to cancel out some units. So first, the only thing actually we have to cancel out is this Kelvin and this Celsius. And you might be thinking, okay, well, how can we do that? Celsius and Kelvin are not the same thing, right? We know that something Kelvin equals something Celsius plus 273, right? But because we're only adding something here, that means we can essentially treat Kelvin and Celsius as the same. So in all your heat transfer problems, you can interchange, I shouldn't say always, but most of the time, you can interchange between Kelvin and Celsius. And so that leaves us with, I'm going to separate the math and the units here. We have minus 0.029 times 10 over 20 times 10 to the negative 3. And then what are our units? So over here we have watts, so times watts. And then we have a meters on the bottom and a meters on the bottom. So I'm going to change that into meters squared. And that unit should make sense, right? We're looking for heat flux, so we're looking for the watts, the amount of power that is dissipated over an area, meters squared. And furthermore, we divided by this area earlier, right? So we should expect Q sub x double prime to have units of watts, like Q sub x, divided by A, and A is meters squared. So we go ahead and do that math, and we get our answer as 14.5 watts per meter squared. And you may be saying, well, what should we do with that negative? Well, we can ignore that negative because it just tells us about directionality. And in this case, because our schematic has been drawn and we know which way the heat transfer is going, we can just say, okay, this right here is 14.5 watts per meter squared. So that's our answer for part A. And now let's move on to part B. So part B, we were asked to find Q sub x. And if you remember from earlier, we said that Q sub x equals minus K A delta T over delta x. We then divided both sides by A, and we figured out that Q sub x double prime, the heat flux, is equal to minus K delta T delta x. Okay, so now what we need to do is we need to get Qx. Oh, you know what? I'm going to ignore that. So you remember from earlier, we have our equation that our governing equation, Q sub x equals minus Ka delta T delta x. And now we can just go back and plug this in. We can say equals minus 0.029 watts per meter Kelvin times A, which if we remember is 2 meters by 2 meters. So we're going to say 2 squared meters. That is going to be 4, but we'll just leave it like that. Times 10, and this can be K or C. I'll just write K here. Remember, they're interchangeable. Divided by 20 times 10 to the negative 3. We could do all of that, and that's meters, and that would give us the right answer. However, we can also take a little shortcut here by realizing that there's a relationship between Q sub x and Q sub x double prime. So Q sub x equals Q sub x double prime times the area. And that should make sense, right? Because earlier we wanted to get this, and what we did is divide by A. So now to get the other way, we need to multiply by A. So I'm actually just going to take our answer from last time, 14.5 watts times 4 square meters. And excuse me, the 14.5 is going to be watts per meter squared, like we have earlier. And those meter squares are going to cancel. And then 14.5 times 4 is just 58 watts. And that is our answer for part B, excuse me. So the last thing, do we have any comments on the problem? Well, the first thing we could write is what we had to consider, that heat flux is not equal to the rate of heat transfer, right? The rate of heat transfer is that Q sub x, although it doesn't have to be an x, and the heat flux was our Q sub x double prime. And this was watts per meter squared. This was how much heat is getting transferred for some area, versus this was just in watts. So how much heat is getting transferred overall. We could also write that heat is flowing from hot to cold, and in this case, T1 equals hot and T2 equals cold. And how do we know that? Well, they told us T1 minus T2 equals 10 degrees Celsius. So this one has to be bigger than this one in order for this one to be a positive number. And finally, we will just note what I talked about earlier, that a temperature difference can be expressed in either degrees Celsius or in Kelvin. And either one is fine. And that's all.